So, welcome to the 12th lecture of graph theory. So, today we are starting with a proof of the theorem we were discussing in the last class, that is, if the connectivity of a graph is sufficiently large, then the graph is k-linked. So, we can formally state the theorem like this. So, okay, formal statement of the theorem I will mention like this. So, we will say that there exists a function f of k such that if G is f of k connected, then G is k linked. This is what I want to show. So, how much should be this function is the main question. So, we will later show that f of k equal to 2k. I mean, you can bring it down to 2k, but we won't prove that because the proof is more complicated. We will just show that some big function of k would be enough. So, we will be showing something exponential in k, but it will give you a feel of what kind of proof it is. And but we need some preparation for even this. So, the first thing we need is this: every graph G contains a cycle of length at least delta of G plus 1, provided delta of G is greater than or equal to. What is this delta of G? Delta of G means the minimum degree. If the minimum degree of a graph is delta, then we do have a cycle with the number of vertices in it as delta plus 1. So, how do we prove this thing? This is an old theorem from Dirac. So, the proof is simple. See, what we do is we consider the longest path in the graph G. What do I mean by longest path? You take a path, and then if it is the longest path starting from this vertex and this vertex, if you look from this vertex, you cannot get any vertex outside it, it is a neighbor of it. So, that means any if there is a neighbor like this which is not in this set of vertices, not among this path, in this path, then we will get a longer path, right. So, this kind of an edge will not be there. What does it mean? But the minimum degree is delta, that is d of x is greater than or equal to delta. So, what does it mean? So, it means that all the neighbors of x has to be here, is not it? So, somewhere here like this. So, this is also a neighbor of course, this is also a neighbor, this is. So, it is possible that there are some vertices in this thing which are not neighbors of it, but all the neighbors of x has to be here. So, this path should contain at least delta vertices, and this x included delta plus 1 vertices. Okay, so, where do we get the cycle now? We can always consider the neighbor which is farthest in this path, and that will give you a cycle, right. For instance, if this is the vertex which is farthest in the path, here 1, 2, 3, you can count delta of them here, including this delta plus 1. If I go like this and come back, you will get a cycle, right. This is a simple idea, very simple idea. So, to repeat, we are saying that if the minimum degree of the graph is delta, then we should get a cycle of length delta in this graph. The next statement we want is this: every graph G with at least one edge has a subgraph H with minimum degree of H greater than epsilon of H greater than equal to epsilon of G, then we are using something called epsilon. What is this epsilon? So, as we have seen, so there are these 2-3 parameters. One is minimum degree delta of G. Among all the vertices, consider the degree of all the vertices, the smallest is the minimum degree. And then there is something called average degree. So, average degree, so sometimes I write as d average, or sometimes as d of G. Average degree of G is essentially the sum of degrees divided by the number of vertices. So, that is sum of degrees of V element of V of G divided by cardinality of V of G. This is essentially 2 times E of G, right, the number of edges in graph divided by V of G. Why 2 times? Because the sum of degrees is double the number of edges, right, 2 times the number of edges. So, here is another one, half of it. Suppose if I take only this much, that means the average number of edges in the graph. So, okay, not like that, it is just essentially the edge, the number of edges to number of vertices ratio. This is called epsilon of G. How many edges are there in the graph? So, of course, epsilon of G is essentially half of D average, isn't it? So, now you know, if the average, suppose your minimum degree is delta, if the minimum degree, sorry, if the number of edges in G is so the epsilon is given, suppose, that means the number of edges by the number of vertices is given. Now, we can always find a subgraph of G such that its minimum degree itself is strictly greater than the epsilon of this. Why is it possible? So, what we are going to do is to kind of concentrate the graph by, so of course, just because the number of edges to number of vertices ratio is high, it does not mean that all the vertices have high degree, minimum degree need not be high, right. So, it is possible that several vertices are of very high degree, but then some vertices are low degree, very low degree. Therefore, while the average degree is high, the minimum degree can be quite small, or while the epsilon is very high, the number of edges to number of vertices ratio is high, while the minimum degree can be small, it is quite possible. But we can indeed throw away these bad vertices. Bad vertices means the vertices which are very low degree, and try to make all the vertices of degree at least epsilon. That is what we are going to do. So, how will we do that? So, the method is like this. So, here is a graph, and its epsilon of G is equal to epsilon. Now, we pick up a vertex whose number of incident edges in it is at most epsilon. Now, what can you do? You remove that vertex. So, when you remove that vertex, how many edges are removed? At most epsilon, at most epsilon. So, one vertex is gone. That means, if initially n vertices are there, now it has become n minus 1 vertices. Now, the number of edges, if it was m initially, it has become m minus epsilon in the worst case. It may be a little more sometimes. So, the reduction of one vertex, the reduction of at most epsilon edges, that means the total epsilon of the resulting graph, say if g dash is the resulting graph, it is not reduced, it is greater than or equal to epsilon only, isn't it? So, but on the other hand, I have thrown away a vertex of low degree, that means whose degree was at most epsilon or less, I have thrown away. I can pick up another vertex now in the remaining graph. If its degree is epsilon or less, I can again do the same trick, I can throw it away, I can remove it from the graph. You throw away one vertex, the number of edges thrown away is at most epsilon. So, for one vertex you are only giving up at most epsilon edges. So, originally the edge to vertex ratio was epsilon. So, we are not going to reduce the ratio, right. So, now by doing this thing, we are kind of concentrating the graph, or in other words, we are throwing away bad vertices, the vertices of low degree. So, in the end, when do we stop this process? We stop this process when we do not get any more vertices of degree epsilon or less. Okay, this will happen before the graph completely gets removed, because after some time the number of vertices itself will go below epsilon. So, how can it even have epsilon neighbors? Epsilon, the total number of vertices epsilon means the any vertex, if you take the degree is at most epsilon minus 1. So, it is not possible to throw away the entire vertices. Every time you are throwing away one vertex at a time. So, therefore, you will stop before the graph completely disappears at some point. At that point, let us call the graph as H. Now, you know that in this graph H, every vertex has degree at least epsilon, right. Sorry, I just made a mistake. So, what I am telling is why will not it become empty? Because every time we are throwing away a vertex, we make sure that our epsilon is same, that means epsilon is same or higher, it does not reduce. Of course, when you reach empty vertex, so no edge, so one vertex, that means no edge one vertex, so epsilon will go to 0. So, essentially it has to reduce if it becomes empty, right, if it, because one by one when the vertices are removing. So, at some point epsilon will have to reduce. So, there will be a point when the epsilon will definitely reduce if it becomes empty. So, at some point it has to stop, right. But then at the point we stop, it is very clear that we are stopping because every vertex has already got degree greater than equal to epsilon, because if there was a vertex of degree less than equal to epsilon, we could have thrown it away without decreasing the epsilon, right. Now, we know that there is a point where epsilon has to decrease. So, therefore, we stop there, that is H, and then this H has degree, each degree greater than equal to epsilon. So, sorry, greater than epsilon, not greater than equal to, strictly greater than epsilon, that is what we are saying. Their minimum degree will become greater than epsilon, sorry, strictly greater than epsilon. The epsilon of the subgraph will be at least as much as the epsilon of the original subgraph, right. So, now we can now we can prove the lemma we want. So, you remember the intention is to prove that when the connectivity is large, you know, the minimum degree has to be large also, right. Minimum degree has to be large. If the minimum degree is large, the average degree is also large, right. If the connectivity is k, minimum degree has to be k, because we have learned that kappa is less than equal to the kappa dash is less than equal to minimum degree, right. And now if minimum degree is also a lower bound for average degree, so the average degrees, so this the connectivity high means average degree is high, then with high average degree we can get a special structure in the graph which is called a topological minor, which is reasonably big. What do I mean by topological minor? So topological minor is some structure of this sort. For instance, it is a clique, but the edges are kind of elongated. For instance, so for in a clique we may see these kind of edges, all the connections here, but in a topological minor we may instead of edges we may see paths. So essentially, so this is called a subdivided clique, right. Subdivided clique, that means all the edges of the clique are replaced by okay, or it is kept as an edge, or it is replaced by paths. So these vertices will not be shared by, this internal vertices will not be shared by two different paths. So we will say that a KR is a topological minor of a graph, G. If we can find this subdivided KR in G, what do I mean by we can find this subdivided KR in G? In other words, we should be able to locate, this is G, we should be able to locate this R vertices of KR in the graph G. There can be several other vertices, but we should be able to locate this R vertices, and we should be able to trace some paths between every pair of these R choose two paths, right. So every pair of these R vertices, that I should be able to trace a path such that no two of those paths intersect in any internal vertex, right. Internally vertex disjoint paths we should get. So this is essentially we should be able to identify KR, subdivided KR embedded in this graph, right. These vertices will be called branch vertices, because these are the vertices. There can be other edges here like this, but we can as well, I mean we can think that they are all deleted, and then we can just concentrate on these things. Somehow this structure is available in the graph. So then we say that this topological minor is available in the graph. So that is what. So if we can identify R branch vertices such that between any pair of branch vertices we can find a path, and no two of these paths share an internal vertex, that means a subdivided KR can be found in graph G. Then we say that KR is a topological minor of G. So in our proof what we need is a topological minor of some large KR, some for large clique, for some KR for a large R, that is what we are looking for. Why do I look for this thing? Because you remember K-linkedness means given any collection of K vertices and collection of K source vertices and another collection of K sink vertices, we should be able to collect between any pair of them like that. So the enemy may give us the pair S1 T1, S2 T2, S3 T3 like that. Now this connection should be possible. So, good thing about topological minor, it is a kind of structure available in the graph with lots of connectivity between among themselves. So, if you get into this topological minor, you can try to connect between each other. This is the point. So, okay, that we will come later. Before, so that is, I just motivated that this kind of structure, finding this kind of structure will help to solve our problem. So, the next statement will tell us that if our average degree of the graph is sufficiently large, we do get a KR top, whichever R you want. We can find if a function h of r such that if the average degree is greater than h of r, then we can get the required KR minor. So, this is what we are going to do next. So, there is a function h such that every graph of average degree at least h of r contains KR as a topological minor for every r element of n. So, we are going to take this function as h of r equal to 2 raised to r choose 2 or something like that. So, we will do induction first on the number of vertices, then on the number of edges. Put r equal to 1. So, r equal to 1, that means we are looking for a k1 which is always available. Put r equal to 2. So, k2, we are looking for a k2. As long as our minimum degree, sorry, average degree is not 0, right. So, there is one edge in the graph, then we do have a k2. Therefore, this induction assumptions are correct, even we do not have to put this much, anyway it is true. So, now let us say that for a r, given r, we will start, the r is fixed now. We are looking for a topological KR minor, but instead of directly looking for a KR minor, we rather would look for a minor of a graph which is a subgraph of KR. Initially, we will say that any graph with m edges can be obtained as a topological minor if, say, if h of r is, that means the average degree is taken to be greater than or equal to 2 raised to m. This is what we mean. So, for m equal to r plus 1, we will do the induction like that till r choose 2. See, when m equal to r choose 2, when m becomes r choose 2, we can see that means when of h of r is greater than or equal to 2 raised to r choose 2. So, we will get a graph, we can get the graph with r choose 2 edges in it on r vertices of case. That is the KR minor of case, KR as a topological minor. So, we just have to go through this induction. We will start with a graph with r edges in it. So, we will have a graph, we just have to, not any graph is not required, we just need one graph, because when m equal to r choose 2, you see there is only one graph with r choose 2 edges on r vertices, right, it is KR. So, that will automatically come. So, our idea is to start with r, and we will show that there exists one graph with r vertices, r edges and r vertices, as a minor if I take the average degree of the graph to be greater than or equal to 2 raised to r. That is true because the average degrees if h of r, the average degree is greater than or equal to 2 raised to r. So, of course, our epsilon is greater than or equal to 2 raised to r minus 1 then, right. And what about our delta minimum degree? See, epsilon is greater than or equal to 2 raised to r, so r minus 1. So, then you can always find out a subgraph of that, the minimum degree is at least epsilon plus 1. So, 2 raised to r minus greater than epsilon, I mean 2 raised to r minus 1 being an integer, we can say that this is, and this is of course greater than or equal to r. Okay. So, put r equal to 2. So, then onwards 2 minus 1, 2 raised to 1 plus 1 is greater than or equal to 2. So, we will get essentially minimum degree is greater than or equal to r. We can assume that minimum degree. So, we will get a cycle of with number of vertices delta plus 1 equal to r plus 1. So, r plus 1 cycle has r plus 1 edges in fact, if you delete 1 from that. So, it's an easy thing to see that we get we can start the induction with m equal to r. We can find on r vertices a graph with r plus 1 edges or r edges, right. Delta is greater than, yeah, we can find. So, this is essentially r plus r edges, because the cycle itself is r plus 1. We can always, since a cycle is a topological minor of any smaller cycle. So, whatever number of vertices we want, we can select. So, for instance, so this is a 4 cycle. So, we can consider as the topological minor of a 3 cycle, because this edge can be considered as subdivided, this edge can be considered as subdivided, and this edge as such, right. So, we just say that topological minor of CR is available. So, that is m equal to r, we start off the induction easily. Now, the next thing is to consider suppose for m minus 1, when h of r is greater than or equal to 2 raised to m minus 1 or less, we know that the statement is true. That means, in the graph we do have a topological minor of some graph on r vertices with m minus 1 edges in it. Now, we will assume that h of r is greater than or equal to 2 raised to m. We want to show the existence of a topological minor with m edges in it, right. So, to do this thing, what we are going to do is to find this is the graph G. So, we will find a connected subset U here, and then this is a connected subset U, and you know, this h of r is greater than or equal to. So, what is epsilon? Epsilon is greater than or equal to, because this is average degree. So, we have 2 raised to m minus 1 as the epsilon, right. Now, we will find out some connected subgraph U of G and contract this thing. What we get is G bar U, right, G bar U. So, when you contract this, the resulting graph G bar U, so this is G dash, so should be such that its epsilon is at least 2 raised to m minus 1. And moreover, we will try to get U such that it is maximal, that means we cannot add any more vertex to u. That means the biggest possible u that we have selected. It is a connected set, two properties. One is it is connected. When I contract it, the resulting graph has epsilon, that means number of edges to number of vertices ratio greater than or equal to 2 raised to m minus 1. So, if we cannot contract anymore, its meaning is that the epsilon might be reducing by that, right. When you try to assimilate one more vertex into u and contract, the total epsilon may be reducing it, meaning several edges may be being destroyed or removed by that contraction process. So, that is why it is happening, right. So, first, but we should ask whether there is any such u at all in the graph. That is there because you can take u as a singleton vertex, and then if you do this contract, g bar u is g itself. So, and then initially g has epsilon greater than 2 raised to m minus 1, there exists some u definitely, namely any singleton vertex will do. Now, you do this thing. So, this is the picture, this is g and this is our u. I am just taking this u, this connected set. So, let us see, and this is maximal with respect to the property that when you contract any more vertex, the epsilon will reduce below 2 raised to m minus 1. Now, you see this has not become one single vertex, right, because epsilon will become 0 then. So, therefore, and also the original graph is connected. Why do I assume that the original graph is connected? Because of course, the original graph, because I am only looking for a topological minor, I can take the connected component with the biggest epsilon, and of course, the biggest epsilon has to be at least as much as the epsilon of the entire graph, which is 2 raised to m minus 1. So, it is unimportant to worry about whether it has several components or not. So, it is connected. So, now say let us say these are the here is the neighborhood of this. So, that means these vertices are the direct neighbors of u, right. Now, this after contracting, this has become one vertex, right. So, it will look like, so here we have this u, this is u, this is entire u, and here its neighborhood, right. So, this is neighborhood, direct neighborhood. This let us call it as h, this induced subgraph on this let us call as h, let us call this induced subgraph as h. Now, what we are interested in is to analyze this graph h. In particular, we are interested to know what is the average degree of this induced subgraph h. Is it possible that the average degree of this graph, or in say let us say minimum degree of this graph is 2 raised to m minus 1. Is it possible that the minimum degree of this graph is 2 raised to m minus 1? Why not? It is possible. Why? Suppose it is not. So, there should be some vertex here, some x here, such that its degree to inside is less than 2 raised to m minus 1, less than 2 raised to m minus 1. So, it to this into this h, right. So, the rest is all going into this, right. Now, of course, this is also connected to this, that is why it is connected. So, in that case, the question is what would have happened if we taken this x also into u and contracted it along with u. Anyway, it is connected to you could have contracted, right. So, why did not you contract? Because we decided to select u as a maximal such thing. So, that making sure that the number of edge to number of vertex ratio for the resulting graph is still 2 raised to m minus 1. So, that is the only reason why we did not do that, because if we do like that, the ratio of the number of edges to vertices will go below 2 raised to m minus 1. But how many, when I am taking this vertex into this, one vertex is reducing of course from this resulting graph, but how many edges are reducing? So, the resulting graph, all these outgoing edges will remain. See, the problem is it is possible that when I take this vertex inside, this one edge will disappear. Also, all the edges which are into this H may become multiple edges. So, I will draw this like this. For instance, this U is connected to all the vertices here already in H, right. Now, this X was also connected, X is pulled into this, but all the vertices of X, these edges will, because this is contracted into one vertex, will become one multiple edge, right. So, all this they will not count anymore. So, we will lose all those edges, but we are losing only less than, because number of edges were only the equal to the degree of x here, d of x, right, plus one edge into u, right. This much only we will use. If d of x was strictly less than 2 raised to m minus 1, then we will only lose 2 raised to m minus 1. But our intention, the originally 2 raised to m minus 1 was the epsilon of g bar u. So, if you move x into that, we are only losing 2 raised to m minus 1 edges, but one vertex is also reducing. So, epsilon will remain same. So, that will be a contradiction that u was the biggest possible we took. We could have taken x also into that. So, that is the reason why x also can be assimilated into u. So, it follows that every vertex in H. So, this is what we wrote here, H in this neighborhood of u here has to have a degree of at least 2 raised to m minus 1 in the induced subgraph, which means that the average degree of that induced subgraph is 2 raised to m minus 1. So, by induction assumption we do have a subgraph, a topological minor on some R vertex graph with m minus 1 edges in it, right. So, this is our u. So, this is the entire neighborhood in H. We should be able to find out some R vertices here, branch vertices, and such that some graph with m minus 1 edges is available here. Now, of course, m is still not equal to R choose 2. If m is equal to R choose 2, we are already done. So, m is not equal to R choose 2. What we can do is, okay, find out some missing edge here, some edge which is not present. Then, of course, this is connected to you, this is also connected to you, and there is a path here. So, and this path has nothing to do with the paths inside here. So, therefore, we can go here and follow this path and come back. So, we got one more edge, that means a graph on R vertices with m edges we got as topological minor here. So, that way the induction progresses. So, in the next stage it become m plus 1 and slowly we will reach R choose 2, and when we reach R choose 2 we got a graph on R vertices with R choose 2 edges in it, which is the topological minor of KR. So, that is the way we prove it. So, this proofs tells us that there exists a if the average degree is greater than 2 raised to R choose 2, we can just call it as H of R. Then there exists a topological minor of KR in the graph. Now, we can look at the final statement. So, now we take another function f of k, this is what I have written. So, we can take this function f of k as h of 3k plus 2k. See, this is to make sure two things. See, the function is greater than h of 3k, means we do have a topological minor of 3k available, because this connectivity would imply that average, the same average degree at least. So, h of 3k is the average degree means by our previously proven statement. We know that there exists a topological minor of 3k vertices in the graph, and plus 2k. If suppose this was small, then 2k would assume that it is at least 2k connected. We are making sure that it is not the connectivity of the graph is not below 2k, in case h of 3k was small number, right. So, but here it is not small number. So, but maybe it is possible that somebody may come up with a smaller value of h of 3k, right. So, it is so suppose you put f of k equal to h of 3k plus 2k, then every f of k connected graph is k linked for k element of n. This is what we want to show. So, how do we show this thing? So, we use this topological minor. So, we are going to show that k linkness now. So, we use this topological minor. So, this is the topological minor available. This is a 3k topological minor, R equal to 3k. So, 3k means 3k vertices. Now, we only want to show k linked. So, let us say we have S1, S2 up to Sk somewhere, and similarly T1, T2, Tk somewhere. So, the point is that this is a k element set, this is a k element set, and here is a 3k element set. Now, this is together S's and T's together is a 2k element set, and the graph is 2k connected. By Menger's theorem, there are disjoint paths from this S1, S2, Sk, T1, T2, Tk to this 3k element set, right. This, if I take this as P and this together as A, right, I do get 2k disjoint paths starting from S1 and reaching somewhere here, T1 and reaching somewhere, so like this. So, of course, because it is AB paths, it will start on each of these S1, S2, Sk, T1, T2, Tk and reach here in exactly, there will not be any other vertex for each path, there will be just exactly one vertex from these 3k vertices. So, it will use up, these paths will use up 2k vertices of these 3k branch vertices, 3k branch vertices of this k 3k topological minor available. So, we still have k more branch vertices left. This k branch vertices we are going to use for our this thing. So, this is our topological minor. So, these are the branch vertices, say, to which Sk got Sk paths came and paths from S1, S2, Sk came and entered. So, these are the branch vertices, say the paths from T1 to Tk came and entered. See, it's these paths need not be long paths, it can be a singleton path also, right. So, these are the ones, and when we select these paths, so and also there are these k vertices left which are not used by any of these paths, right. But when we select this path system, so starting from S1 to Sk and T1 to Tk and reaching this thing, we have a various possibilities. There are several possible collection of paths available. Among all the collection of paths available, we will pick up the collection of paths such that the number of edges from outside this 3k3 topological minor, sorry, k3k topological minor, this setup, this is a some kind of a connector box, right, branch vertices and the topological, these paths are there, right. So, we would like to minimize the number of outside edges. So, of course, we will have to use something, maybe somehow we have to reach here, but once you reach inside this system, we would like to use as much edges from the system rather than from outside, right. So, among all the possible collection of paths that connect this S1 to Sk and T1 Tk to this box, this topological minor, we would like to take the one that minimizes the number of edges used from outside this topological minor. So, if that is what we want, then so we will get this picture in fact. So, these are the end vertices of this paths coming from S's, these are the end vertices of the paths that come from T's, and these are the vertices which are outside. These are the vertices which are outside. Now, what am I going to do? See, I will show you how to connect S1 to T1, S2 to T2. S1, this path will come and end here. I will show a way to reach T1 here without using any other paths, right. And similarly, I will show a way to reach from this is the path which reaches from S2 and reaches inside here, from here to here and then reach to T2 and so on. So, for that we use this one. So, we can also name this as U1, U2, U3, UK, right. Now, so for one example, we can take U1. This U1 is one vertex which is not used up by the n vertices of the T paths or S paths, and then we look for the top edge, the end point of this path coming from S1. It reached here, right. Somehow it reached here, I do not know. So, it is it may be how we reached, this is the path. How it might have reached, we have no idea. It's possible that it might have traveled a long way and somehow it reached here, I know, right. And similarly, I will consider the so this I can use as I can call a name by x, say x1, this is x1 to x1. Similarly, here I may be able to find out the vertex y1 to which the T1 path ended. So, it may be started and then somehow it ended here. I do not know how it ended, right. It reached here. Suppose these are the two vertices S1 reached, and then now we consider these paths, these two paths in the topological, inside the topology. This is a U1 x1 path in the topological minor, U1 y1 path in the topological minor. These paths are available, but it does not mean that no other path has contaminated this path. See, if it was just like this, I could have followed this and then this path and this path is disjoint. So, I take this, I take this, I would have got a S1 to x1 to U1 to y1 to T1 path, but that is not necessarily pure. It is possible that when I try to use it, there I may see some path using a vertex here, some other path using a vertex here and all, some path may be using some portion of here and so on. So, what do? I want to examine this. I start from here and scan this portion, right, this portion until I see the first vertex on which some path hit. This path need not be the path coming from S1. Suppose something hit here, right. Now, the question is, so this path, whichever path it is coming from some SI or TI, why did not it come directly to U1? Because this entire portion was empty, I could have followed this thing. So, why should it come? Why isn't it? You may ask why it could have gone somewhere else also. But if it ever went out of this thing, then it will use an edge to go out, right. For instance, it might travel here and get out, or it may get out from here itself. But whenever it gets out, it will use an outside edge which does not belong to the topological minor. On the other hand, if it had traveled to here, then it would not have used any more outside edge. You would have reduced the number of outside edge used by that. So, it means that it never gets out once you touched it, once this path touched it, because it did not follow this path, it means that it had followed this path. It never went out, but rather it went to this side. But then if it went to this side, so right, if it went to this side, it means that it should totally reach all the way to x1, but if it reaches x1, then it is the path which was coming from s1, because once it uses all these things, how can s1 reach x1, right? So we end up concluding that the first path, when I am tracing from u1 to x1, moving from u1 to s1 and looking for a path hitting it, so the first path which hits it in fact is the path starting from s1 and reaching x1, right, because x1 is reached by the path from s1 only. So that is it, this is the path, right. So we can mark it with another color maybe. So this is a path coming from here, this is from s1. Similarly, by a similar argument I can say that if I trace from u1 to y1, the first path I hit here, right, the first vertex I am seeing here as hitting as an outside path hitting there should be the path which goes all the way to y1, because otherwise it will get out of this thing and it will increase the number of edges used from outside. Why it could have come all the way to u1, right, rather than why should it go out and reach somewhere else. If it just came, u1 was empty, u1 was not used, it could have come backward and used up u1. So therefore it should be going all the way to here and reaching y1, and that is essentially t1. So we can mark that it is the path coming from t1, this path is coming actually like this, right. Now you know what to do. So if you want to reach from s1 to t1, you will follow this path, reach here, and instead of going to this side, we would rather take this side and then come this side, and then we will follow this path. This is what we will do, right. So we can mark it with a different color, maybe this is the way it will do. So now you know that this was empty part, so we are not using any we are not encroaching into anybody's territory. So no other path is using these vertices. This was exclusivity to s1 to x1 path and t1 to y1 path, and this was empty, this was not used up by somebody else. Like that for each s1 t1, s2 t2, we can use another u2 to connect them together. For s3 t3, we can use the third vertex u3, the unused vertex. That is why we had 3k vertices in the topological minor first, because this k extra vertices we wanted to use, right. So we can manage to connect all of them together. So it follows that, so we can, given k source vertices s1 to sk and k sink vertices t1 t2 to tk, then we can connect every pair t1 s1 t1 s2 t2 with disjoint paths. The only condition we wanted was the connectivity was to be at least fk being h of 3k plus 2k, this plus 2k for connectivity, to telling that the connectivity of the graph is 2k, and h of 3k to tell that there exists a topological minor with 3k branch vertices in it. The topological subdivided 3k clique is available in the graph, and we know what is the value of h of 3k. So the earlier theorem told us that if you put h of 3k is around 2 raised to 3k choose 2, then we will get one such thing. Big number, but we are only claiming that there exists a large value of connectivity such that once you have that kind of connectivity, we will get the k linkness. And finally, to conclude, so we will mention that we already mentioned it. So that this theorem is proved that so it's much more its improved version is, let G be a graph and k element of n if G is a 2k connected graph and the average degree is greater than or equal to 8k, sorry, not average degree, the epsilon means average degree is 16k, then G is k linked. This is by Wallen and Thomas. The earlier theorem was by Jung, J.U. Jung, and Larman and Mani. So that is from the 70s. So this is a recent theorem, 2004 or so, 2004 or 6. So but then the proof is a little longer, but D still has the proof in its in his textbook, so students can read it from there. So, that is all for today. So, in the next class we will start with coloring. Thank you.